elevator and another elevator, and now you're 20 stories up in the air inside a control room. And we stay there hours and hours on end, really all night long, sometimes 12, 14-hour shifts. And I like this picture because it demonstrates one of the great things about the LT, an incredible opportunity here. Now, in the foreground, Arturo Gomes-Ruiz, a staff member of Inaue, is helping to control the telescope. But you know who's driving the telescope? Erica Keller was an undergraduate student at Mount Holyoke College who was on an observing run for 2 weeks. I've observed the telescopes all over the world, on the largest telescopes in the world, the Keck telescopes in Mauna Kea, Canary Islands, Chile. I have never been at a large telescope where an undergraduate was even really in the control room, let alone allowed to control the telescope. Here, Erica was controlling with tremendous skill and confidence for weeks on end. It's a tremendous opportunity for our students to be able to engage, not just in research with the data, but actually to go to the telescope and get the data. There is no experience quite like going to the mountaintop and understanding first the hardware, the instrumentation, but also the experience of being out there on the mountain, collecting real light from the real universe. There are Erica and Arturo and I on the very summit with the telescope in the background. And here we are on the catwalk with one of the very able assistants at the telescope. This gives you a sense of the scale, the gigantic scale of this dish. And maybe you arrive at night at the telescope, and we do have a wall, but you notice the gates open, and so you're and Alfonso Serrano's name is on there, you may notice something. Now, if you look over in this direction, you'll be looking out over the cities and towns far below. This is a time-lapse film showing the rotation of the sky, speeded up hundreds of times. Of course, the rotation of the sky due to the rotation of the Earth. And if you turn your head now, you'll be looking towards Pico de Orizaba. Notice the little twinkling lights. Those are the headlights of climbers climbing the mountain in the darkness as dawn, as the sun rises over the mountain. And if we were to keep our vision fixed in that one direction, here you would see very clearly the rotation of the sky, the apparent rotation of the sky, due to the rotation of the Earth. There's the North Star in the middle there. And of course the telescope has to move as well. And we'll see that shortly. Well, there's another wall, but it's again, it's permeable. So there's our telescope now tracking objects across the sky. We're looking at hours and hours of real time compressed into a few seconds here. So of course the telescope doesn't actually move this fast, but what it's doing is moving from object to object and then tracking objects across the sky, collecting this faint radio emission from distant galaxies and star-forming regions in the Milky Way. And there's the Milky Way itself, our own galaxy wheeling across the sky as the Earth turns. There's some thin clouds passing by here, but the LMT can see right through those. Thin clouds, no problem at all. Our short wavelength radio really has a great ability to see through those thin clouds. Thicker clouds, not so easy, but notice where they are, below. We're looking down on the tops of the clouds here. Those clouds are no problem for us at all. It's one of the main reasons that the LMT is up at this elevation where we're above more than 90% of the atmosphere. And here's the sun rising again over the landscape. And this view shows you now, looking towards the south, the south pole of the sky is just below the horizon, the center of those circles there. That's because the latitude of the LMT is basically the latitude of Hawaii. We're in the tropics. We have access to both the northern sky and the southern sky. Another great reason for putting the telescope there. We have a tremendous access to practically the entire sky total of objects. Now, it's just phenomenal to think that this dish weighs 2,500 tons. 2,500 tons of steel, groaning and shifting under the weight of gravity, and yet maintaining its shape to 1/10 of a millimeter, thanks to its active surface. And I love to think about the telescope as a light bucket. We always talk about telescopes as light buckets, and here I feel as if the starlight is actually falling into the bucket right before our eyes and being collected. And to think there are people in there right now working the computers that control the telescope and control the cameras. And so back I go into the telescope and work on a project. Now, what's the project? project we're working on. This is just one of dozens and dozens of projects. This is one led by my friend and colleague, Min Yun, but I really want to emphasize that practically every project, as David just said, practically every project done on the LMT is collaborative. And I really don't know if there are more of our Mexican or more of our American colleagues on this particular project, because immediately I know, Yasir's got to be on this project, David's got to be on it, we're probably going to need the help of Milagros and David Sanchez and so on. So it's just normal that on every science project we collaborate closely. And this particular project, this thrilling project, is finding and studying the very, very brightest galaxies in the universe. And the amazing thing is they are practically invisible in the kind of light that we can see with our eyes. The Hubble Space Telescope would have a very, very hard time finding these galaxies, and yet the LMT finds them very well. I want to emphasize also, again, this project was conducted largely, again, with Min's directorship, by an undergraduate student here at UMass, Kevin Harrington. Kevin is now a graduate student in Germany, but he, working with Min and the rest of the group, was able to sift through thousands and thousands of galaxies discovered by a satellite called the Planck satellite orbiting around the Earth, and then to confirm that, in fact, they were very, very bright, very distant galaxies, by using the LMT to measure their distance. This was a key part of the puzzle. Without measuring the distances to the galaxies, there was no way to know how bright they really were. And the only facility that could do that was the LMT. When we didn't have that capability, all we had was little fuzzy blobs in the sky that were very difficult to squeeze any detailed information out. These are optical pictures on the left here with an practically all-sky telescope that delivers beautiful images, very high-quality data, and yet it could barely detect our targets. But thanks to some clever sleuthing, we were able to figure out, these are probably the needles in the haystack that we're looking for, but it was only LMT that could confirm it. And it was LMT that provided the curve, the graph on the upper right shows how much light is coming out at different wavelengths. And that great big bump there, that mountain in the curve, those are the points contributed in the millimeter wave, where the LMT really provides the crucial data. And it shows, while the galaxy is faint in optical light, it's super bright in the infrared. I see Alex standing up. So I'm going to zip through a little bit of this here and say, what do we expect to see if we were looking in a nearby universe? We might expect a galaxy of 100 billion stars like this, or pairs of galaxies crashing together to form a great big burst of star formation that would show brightly in the infrared. This is what we might expect to see for our galaxies at the very great distances where we know they are, which is looking very far back in time. But we didn't know for sure until we trained Hubble Space Telescope on them. And this is what we found. Any astronomer looking at these pictures will say, that's a gravitational lens. Wow. And that's a gravitational lens. And that's a gravitational lens. All of these images here are suffering or benefiting from this particular phenomenon that Einstein predicted 100 years ago, where a massive thing will bend space-time and warp light that passes around it. And you're all familiar with this. If you pick up a wine glass, preferably an empty one, turn it upside down, and look at the candle on your tabletop at the restaurant, you'll see the candle take on all kinds of funny shapes as the wine glass warps the view of the candle. Well, we have the same thing happening in space. We have nearby galaxies that have a lot of mass that bend space-time, and they warp the view of the distant galaxies behind them. And that's exactly what happened here. Here I'll point out the work of Alison Reina and Patrick Kamenetsky, who's sitting right here, who was analyzing these warped images to try to decode them and figure out what is the nature of these monster galaxies that the LMT has helped uncover. What fuels them? What powers them? How do they get their huge bursts of star formation thousands of times brighter and more active than the Milky Way galaxy? This garnered a lot of attention. This result was in hundreds of news media around the world. And I'll just leave you with this picture showing the Hubble image in the background that gives us a sharp view of something that's very difficult to find, overlaid with these contour circles from the LMT. And you'll notice in in each case, it's not always centered on the bright thing in the middle. The bright thing in the middle is the lens, that's the wine glass. Notice how in every case, the circles are centered on sometimes a faint little fuzzy thing. That's our target, that's our distant galaxy in the background, our super bright, infrared bright galaxy that the LMT has helped find. Thank you very much.